So I'm working on a book called Correct by Design with TLA Plus. So TLA Plus is this sort of amazing language slash technology I started trying to get familiar with fairly recently. It is so cool that I decided I should probably write a book for it. And then so the book is free. It's on under my GitHub account. Feel free to check it out. And then so hopefully this will result into sort of maybe a set of a video series on TLA Plus. And then so this being the first one. Yeah, so I guess before I start, I should probably talk about why, right? And then like why this is so interesting to me, right? So years ago, I worked on so this is part of my book, right? So years ago, I worked on a proprietary low power processing or low power processor in embedded system. And then so low power system being a low power system, the intent for that is for it to basically progressively put the device into low power state, right? It may execute, tens to hundreds of instructions based on, the various, basically the power state the operating system wants us to put the device into, right? And then it's the usual, right? Like, it would turn off IP-A, then turn off IP-B, then turn off the power island to the IPs, to save power, really, right? But then the problem is, well, maybe not the problem, but like the low power processor in general, because it's a low power system, it has very limited debuggability, right? The whole point is once it's in low power state, all the debug port or all the ports, including debug port, should be powered off, right? And as you can kind of imagine, this was challenging, right, from a debugging perspective, right? So again, right, like the microprocessor would run like hundreds of instructions, and then in the later on in the low power transition, we try to access accidentally the AXI bus when the memory interface has been shut off, it results in a hang, right? And this was impossible or nearly impossible to debug, right? Because you can't attach to the debug port of the device because the port has been shut off, right? And then so now the developer is sort of left with just siphoning through tens to hundreds of instructions, trying to figure out what a violation is really, right? And again, right, like this is not intuitive, right? In the sense that like it's not normal or not intuitive for humans to be doing this kind of work, right? Like it was challenging, right? And then whenever we make changes to these code, it was really hard to guarantee that like do we really get it right? So fortunately, it was a fairly simple processor, right? It was only had like a handful of instructions. So I was able to create basically a simulator to simulate execution of the instruction, and then basically track the processor state throughout the execution, right? And this is really cool, right? Because now at every single state, at the end of the state, I could start checking for violation, right? So, I have turned off, the power island already, and then the subsequent command tries to access the AXI interface. That's not okay, right? It should fail, right? And then so the simulator was able to exhaustively confirm basically every possible code path that the the implementation is concrete, right? Like when it passes the emulator, we know we have very high confidence on the quality of the code. Then we can deploy on the actual target, right? So this itself was actually a fairly interesting experience, right? Because to generalize, we can really model an arbitrary, a system as a set of states and a set of invariants that must be held, across all states, right? And then the challenge is the complexity of the system usually grows, pretty quickly, right? As you introduce more states, that means you possibly have, every new state you add, the nth state means that you possibly have n transition associated with the state, right? Depending on the complexity of the system. And then so like this is like very hard to keep track of from in anybody's mental, like in anybody's head, really, right? But then the problem is, in our line of work, there are like very, a lot of engineering challenges or engineering problems that are similar, right? Like that have a large number of states, right? Like think about like lockless queues, wave-free data structures, distributed system, OS schedulers, consensus protocol, right? Like so on and so forth, right? And then so it's hard, right? Like you could try to write unit tests, right? But unit tests are not, in my opinion, good enough, right? Like it's kind of like plowing through a minefield, right? You could, maybe make sure that a certain path you take are good, right? But you could never be sure it's 100% concrete, right? And then so really the problem comes down to how do we produce a system that is correct by design, right? This is actually a generalized problem, right? And then so fast forward to now, right? So I stumbled across TLA Plus, where I was looking into basically distributed system design, and then this is exactly what I was looking for, right? This solves the problem in a generalized sense, right? So TLA Plus is this basically invented by the Turing Award winner Les Lambert in even around the 2000s, right? And then I'm of the impression that it didn't really caught on until about the past decade or so. And then I think it's because in the past decade or so that the complexity in our industry finally caught up, right? We're talking about like big data, distributed system design, all these kind of things. Now it's really, you can't really keep catching the problem and fix it until it sort of works, right? You really need to make sure the system is correct by design, right? And then so now I start to seeing a lot of instances where like this technology is being applied in a fairly successfully fashion, right? And then fundamentally, I think the problem is as humans, right, as mentioned earlier, our brain isn't really, our cognitive system is really more designed for sequential reasoning, right? When you have a cluster of servers that could all act independently, it's hard for us as human to reason, how they could all interact in any sort of combination or permutation, right? And then or maybe take a simpler example, right? Even for a single producer, single consumer queue, right? I think that's more of the class example that we sort of figure out how to do, right? But then the more complex one, right? Single producer, multiple consumers, right? Like all the possible interleaving patterns, right? How do you, well, what if one laps the other, right? What if you have the readers competing to reserve on an index, right? What if you have a reader that is super slow, another one is super fast? Like what if one is holding up by the other, right? Same thing with OS schedulers, right? How do you make sure all the tasks are scheduled in a fair fashion, right? And then so again, right? Like the anti-pattern that you usually see in the corporate environment is we just keep, we'll throw something in, we'll check in the code, it probably works, whatever, right? And then like basically user whomever will keep stop, like we just keep hoping the bugs stop coming in, and that's when it's good enough, right? But then that's, in my opinion, not really good enough, right? Like we really want to make sure we design stuff right? So good, right? So now what is TLA plus, right? So I've sort of highlighted that I believe this is the right solution. So TLA plus is a system specification language, right? It's meant to sort of capture, I guess, the high level description of a system, right? Without the implementation details, right? And then I guess one of the cool thing about TLA plus is it uses mathematical notation to sort of represent a system, right? And then it might seem a little foreign at the beginning just because it's not your typical programming language, but it's precise, right? That's kind of the beauty of if you go through. So Leslie Lampert did write, a book called Specifying Systems that you could consult, and this is kind of thing that he was highlighting in his book, right? Like the language, the notation is mathematical, right? Like description is precise, right? It's unlike the English language where there's ambiguity, when you describe things, right? And so once you sort of describe the system using TLA plus notation, it's really describing a collection of states, right? And then so maybe in another video we can go through. I'll provide some examples of what that actually looks like. But really, it's a set of state description, really, right? So you could say that this is how we bump this number, right? And then under this circumstance, right? And then basically now we can construct you're describing a system using basically a state diagram, right? And then so now, once you have the state diagram to describe the system, you can now check for invariance, right? And invariance can be applied on a per state basis, right? So say your system has like 1,000 states, you could say that for every single state, the value, the permittable value, for a certain variable has to be within certain range, right? So these are things you can check, right? You can also check for liveness property, right? Like, so that would be like, a certain behavior for a sequence of state, right? So think of, consensus protocol or gossip protocol where you expect the cluster to, converge towards a certain value, right? And then so that is, like invariant that is upheld across a set of states, right? Because you need to sort of, audit the behavior, make sure that the system is going towards a certain direction, right? That's more than one state, right? And that is, liveness property you can describe in TLA plus as well, right? So hopefully that provides enough interest, I guess, right? To sort of like provide motivation as to why I believe this is super cool, right? So you can either, keep reading the book. Right? Again, the book is free. It's on GitHub. You can feel free to check it out. There's more, examples down on how, examples how to write TLA plus, how to verify a spec written in TLA plus, right? And hopefully I'll try to find time to, create more videos on the other examples in this book. Right. Thanks.